cubic surface for finite fields.
Hello, so thank you very much for inviting me here. I've never been to Russia before. I'm very happy to be here. I have a lot of sympathy now with Russians who try to apply for visas to come to the UK after going through the reciprocal process. Okay. So everything talk about this talk is joint work with Barinder, Banwait, and Francesc. So, yeah, I'll just start with some basic facts. I mean, probably everyone knows already, but anyway. About cubic surface. So, cubic surface given by, well, what coordinates want to use? So, zero locus, homogeneous polynomial of degree 3. In P3, so this is going to be my cubic surface S, and I'm going to be working over a field K, and S of K is going to be the set of rational points of S over K. So just the points in projective space, coordinates in K which satisfy this equation. And we're going to be particularly interested in the case of a finite field and what happens there. So I'll just start off by showing you some of the really amusing stuff that can happen over finite fields. There's a cool film due to Swinnerton-Dyer from 1979. So it says, let S be above cubic surface over K with, okay, smooth. I'm not going to be interested in singular cubic surfaces in this talk, or I'm only going to care about smooth cubic surfaces in case I forget to mention anyway. And it has a property that it has exactly one rational point. There's only one solution. Then your field must be the finite field of two elements, and your surface must be only one possible choice, must be isomorphic to the following one. It's x0, x3 squared plus x0 squared, x3 plus x1 cubed plus x2 squared, x1 plus x2 cubed plus x0, x1, x2 plus x1 plus x2, x0 squared. So yeah, so up to isomorphism, this is the only smooth cubic surface with a single rational point. And the rational point itself is very easy to find. It's just, you set all coordinates equal to 0 apart from x3. All coordinates equal to 0 apart from x3. So, very funny theorem. Anyway, I find it very amusing. Okay, so the problem which motivating us, so Serre has posed, I'll state a vague version of the question, I'll state a more precise version later, but Serre's question was, what are the possibilities for the number of rational points on the cubic surface as K varies over all finite fields. Well, what I mean is, probably a better way to say it would be, you're given a finite field which is fixed, and you're saying how many points can a cubic surface have over this finite field. That's probably a better way to phrase it. So it's what are all the possibilities which can arise of all finite, yeah.
Do you fix characteristic?
Pardon?
Do you fix characteristic?
No, just go wild, you know. You want a complete answer, I mean, all finite fields, what all possibilities you can get. Yeah. I think 2012, so Serre, he posed this question in his book. That's a book called Lectures on NX of P, which is quite a cool book about studying rational points on varieties of finite fields. Anyway, so this is a problem, motivating problem. Before I get into details, I'll just again recall some things about the geometry of cubic surfaces. Okay, so S is smooth cubic surface over field K. So over the algebraic closure, S is a blow-up of P2 in 6 points in general position. So general position is no 3, 9 align, no 6 line a conic, and it has 27 lines. Famous classical theorem. Where's the board? I use this, do I? Okay. Yeah, and the lines you can describe in terms of the blow-up model, like you get 6 lines for the exceptional divisors of the blow-up. 15 of the lines come from lines between 2 pairs of points, and the other 6 come from conics through 5 of the points. But you know a little bit more about the 27 lines, namely you know exactly their exact configuration, namely how they intersect each other. So what I mean is the following. So you can associate a graph to the lines on the cubic surface. It's called G of S. So you have one vertex for each line on S, and you have edge between vertices if and only if the lines meet. And one of the awesome things about this graph is it's independent of your choice of cubic surface. Doesn't matter which one you start with, you always get the same graph. So it's isomorphic to a graph I call G, and this can be defined abstractly in terms of the E6 root system, but it's classically called a Staefele graph. So the kind of configuration. I should say, I mean, what this says is, given any 2 lines, somehow the configuration is fixed. But if you look at collections of 3 lines, they can definitely vary. If you change cubic surface, namely, some cubic surfaces have, you know, special points where 3 lines meet called Eckart points, and definitely not every cubic surface has one of these. But if you're just interested in incidences between pairs of lines, then this is really independent of your cubic surface. And this graph has a very large automorphism group, namely it's isomorphic to the Weil group of E6 root system. It's completely irrelevant for us in what follows what group this is. All that matters is just some explicit group we know everything about. In particular, we know the number of elements in it is 51,840. So it's some large groups. This means there's lots of symmetries in the lines on the cubic surface. I mean, yeah. Okay, great. So that was telling you what happens over the algebraic closure. Now, if your ground field K, I mean, your cubic surface might not be a blow-up of P2 in a collection of rational points, definitely, not even a collection of points which are invariant under the Galois action. I mean, if you blow up 6 points in P2 which are invariant under the Galois action, then yes, you get a cubic surface, but not every cubic surface arises this way. Moreover, you know, there's cubic surfaces which are non-rational. The Swinnerton-Dyer example I read on earlier, this cubic surface of finite field of order 2. It's not rational over F2, even though it becomes rational over the algebraic closure. So, you know, hope of understanding in the block model, but you always have the 27 lines, at least over the algebraic closure. And, yes. So, I find the graph of lines of my surface over the field, smaller field, to be just the graph of lines when you base change to the algebraic closure. And this comes with an action of the absolute Galois group. I mean, really, I guess, I mean, yeah, I mean, it comes with an action of the absolute Galois group of your field on this graph. So this is a good way to understand cubic surfaces of a non-algebraic closed field. So you look at the Galois action on the lines and see how it moves the lines around, and it tells you something about that cubic surface. And in particular, since we know the automorphism group of the graph is the Val group of E6 root system, you get a map. But I mean, the automorphism group of the Schläfli graph, it could be defined abstractly in terms of E6 root system. So this is the Val group E6 root system, but there's no canonical choice of isomorphism here. I mean, you have to choose, isomorphism to graph, you have to choose like an ordering of the lines to say which vertex goes to which vertex. And if like linear algebra, analog is, you have to choose a basis. And if you choose, different bases, then this corresponds to conjugating. So anyway, the upshot is that you get a map like this, which is well defined. Only up to conjugacy. Because you need to choose an isomorphism with a Schläfli graph, and there's no canonical choice. Different ones conjugate. So you get somehow you get a conjugacy class of subgroups in this Val group of E6. Okay, now for the rest of the talk, we'll look at the case of finite fields. So here, absolute Galois group of a finite field is generated by, so K is going to be FQ, finite field of Q elements. You have the Frobenius element in here, which sends an element smaller field element here. The algebraic closure X just goes to X to the power of Q. And the Frobenius element generates the Galois group topologically. Namely, if you take all powers of the Frobenius and then take the closure in here, it equals the whole group. So what happens over a finite field is, so with this construction here, now when we do it, so we get a map. Wait. So if you look at the image of the Frobenius under this map, which I'll boost by denotation, just denoted by the Frobenius again. So it's Galois action. You look at the image of the Frobenius in here, you get an element to the Val group E6. So you get a conjugacy class. Of the Val group of E6 root system. So denote this by C of S. So the upshot is, smooth cubic surface of a finite field, you can canonically associate to it some conjugacy class of the Val group E6 root system, which tells you about the Galois action on the lines.
So can you say again, what is the notation? Is it CS?
CS, yeah. There's a subset.
And why is it CS? Conjugacy?
C, I mean, it's just notation, so I can call it whatever I want.
Close.
It's a conjugacy class. I mean,
So S stands for plus. Yeah?
S is surface. C is class, S is surface. Yeah. S is my cubic surface, which was somewhere. Great, now I'll start using this information to study this problem of Serre on number possibilities for points. So the first lemma says you can calculate the number of points on your smooth cubic surface finite field as follows. The number of points, it's 1 plus as q plus q squared, where this as is the trace of the Frobenius element a q acting on. So you look at the Picard group of the surface of the algebraic closure. So the Frobenius element acts on the Picard group and allows you to calculate the number of points, and the proof is nice, so I'll just give the proof. So you want to know how many points. I think this proof's originally due to V, I should say. Yeah, I think it's due to V. To understand the set of points on your cubic surface, so you look at the points over the algebraic closure, and then look at those which are invariant under the action of Frobenius. So the points, rational points are those which are invariant under the action of the Galois group. Now you can apply Lefschetz trace formula. I should probably say, yeah, okay. The result is originally due to V. Probably he didn't use his exact proof. I mean, I'm going to use the proof that Groff and Dick would have given. So you have Lefschetz trace formula for et al. Cohomology. Because yeah, I'm studying the set of fixed points. I've got this group element acting on the set of fixed points, which you can do using Lefschetz trace formula. So I get the sum from I equals 0 to 4. So it's alternating sum of the traces of the Frobenius element acting on on the ith cohomology group of the surface of the algebraic closure, and this is for some L, which for some L which is prime, which does not divide Q. So this is et al. Cohomology. So I mean, we need to use et al. Cohomology because we're working over a field of positive characteristic. Okay, great. But now, all these okay, we have a field of positive characteristic, but any cubic surface of a field, finite field lifts to a cubic surface of a field of characteristic 0. You just look at the equations and lift the equations. So you can calculate these et al. Cohomology groups from the cohomology groups of characteristic 0, which are incredibly well known. So, I mean, the first one, oh yeah, 0th one, it's just got dimension 1. In odd dimension, these cohomology groups are trivial. For the middle dimension, it's the Picard group, but there's some subtlety where you have to take a twist. So this one corresponds to performing a take twist, which basically means you just have to twist the Galois action by suitable cyclotomic character. And then the last one is again one-dimensional, but the Galois action isn't trivial in this case. It's again, there's some take twist knocking around, which was factor 2 means. And so the upshot is, you get, this gives, well, it gives a result. So the 1 comes from, I mean, I hope it's clear, the 1 comes from this one, the q squared comes from this one, these terms don't contribute, and then the middle term gets a trace of Frobenius. Great. So now we have an exact formula for the number of points, and you can use this to now classify the possibilities can occur. So Serre did this as one of the things that motivate his question. So this trace of Frobenius, A of S I'm calling over there, there's only finite many possibilities for it, namely, it could be -2.
This works for any rational surface.
Yes, yeah. He works for any rational surface. Yeah. Geometrically rational surface, yes. Yeah, so the least possible value of the trace is -2, and you can have everything up to 7 apart from 6. So I'll call this set capital A. And now the proof is just brute force, namely, we need to understand how the trace of Frobenius acts on the Picard group. But we also know the trace of Frobenius acts via a conjugacy class of Veil group E6. So there's only finely many possibilities. It means there's a finite group with finely many conjugacy classes. So you just look at all possibilities there are. There's a classification of conjugacy classes of the Veil group E6 root system. You just go through all possibilities, there's finely many, look how they act, boom, and this list pops out. I should say, just out of interest, there's only 25. There's 25 conjugacy classes, and you can do this. You can enumerate them all in Magma in like less than a second. It's very standard, computation for computer algebra systems.
So the Swinnerton-Dyer example corresponds to -2.
Yes, yeah. So in particular, you see, from this formula, if you want if you combine this with this, if you want there to be a single rational point, the only possibility is F2. That tells you that already. But then, so if you want a single rational point, the only possibility is F2. But then, Swinnerton-Dyer also proves a strong claim there's actually just a unique such surface of F2. Okay, now I state the actual question of Serre. So it says given a possible trace, some A in this possible list of possible traces, and Q a prime power.
I'm sorry, I understand that you can use classification and so on. Is there some reason why 6 is excluded? Is there some...
Yeah, that's a good question. Yeah, and I don't know a good simple, I don't know a good simple explanation.
So similar to what please. And again, then you find order. 3, 6. Remember.
Yeah, I guess so. Yeah.
Trace 6 is trace 7 minus trace 1.
Okay, anyway, okay, so it says question, So given a possible trace and Q of prime power, does there exist S over this finite field with the trace of Frobenius equal to your given trace? The answer is no, but Serre knew this because there's finally many cases you have to rule out where it doesn't happen. But what you want is obviously a complete classification of all possible traces of Frobenius and finite fields. So Swinnerton-Dyer first looked at this. And he handled the kind of extreme cases, namely those at the extreme edge. So for -2 and 5, the answer is yes. For all prime powers Q, such cubic surfaces exist. The most extreme one of 7, it's yes, if and only if Q is not equal to 2, 3, or 5.
I think this is just the blow up of like 6 actual points over
2 defined over the field, right?
This one, yeah. So the case of maximal trace is like the split cubic surface. So it's those which is a blow up of 6 rational points on there.
In this case, you just don't have enough in general position, right?
Here.
For Q equal 2, for instance.
Yes, yeah, exactly. Yeah. I mean, you can rule out Q equals 2 much easier. It's basically I think even in the I think in this case, yeah, Q equals 2. If such a cubic surface would exist, it would have more points than the ambient P3. So that also rules out. It can't. Yeah, it also rules out.
Well, like P2 has 7 points, so it's but you cannot choose 6 in general position.
Yes, yeah, exactly. Yeah. So I mean, well, yes. Anyway. So I'll start with the first theorem, which basically handles the remaining cases. So let A be in here, not the extreme case, A equals 7, then there exists S over FQ with the given trace of Frobenius. So basically, the only trace of Frobenius which can't occur over a given finite field is the largest one, or trace 7, which can't occur over finite fields of order 2, 3, or 5. Great. Now I'll explain the proof. So I say, yeah, one amusing thing about this is, it's somehow clear you need to ignore small primes and small prime powers. But yeah, I mean, 4 is allowed. 4's fine in this list, but 3 and 5 aren't. And I'll try and explain why that is in our proof. Okay, so we need to construct cubic surfaces with certain properties. We do this. This is a workshop of birational geometry. We do this by blow-ups. So the following. So let X be a smooth projective surface. Surface over finite field of order Q. Oh yeah, and X is going to be a closed point. So not necessarily a rational point, but still a point whose residue field is finite. Then, if you want to know how many points the blow-up has, so if I blow up capital X, little x, and count the number of points, I get number of points on X plus Q if the point I blew up happened to be a rational point, and otherwise you don't change the number of rational points. Yes, maybe if you're not familiar with closed points over non-algebraic closed fields, I mean, how you should think about them is you should think about Bud as being like a Galois invariant collection of points over finite field extension, if you like. You look at some finite field extension, take a Galois invariant set of points there. This is defined as a set over the smaller field, and you can blow it up and still get a variety defined over that smaller ground field. So the proof's very easily. I'll just say it in words. Okay, in the first case, what do? You remove a rational point and you replace it by a copy of P1. And P1 has P plus 1 points. Q plus 1 points. So you remove 1 and add the Q plus 1. In this next case, you don't add or remove any points. I mean, you're removing a closed point, which is not a rational point, doesn't contain any points. You're adding in some copies of P1, which are commuted around by Galois and don't meet each other. You're not adding any more points. So nothing is added nor removed in the last case. Okay, now hopefully the proof strategy for film 1 should be clear, at least for some of the easiest cases. So the number of points in P2 of FQ is 1 plus Q squared. The number of points on our surface is 1 plus the trace of Frobenius Q plus Q squared. And we just have to blow up the correct collection of rational points and closed points to make sure we hit the correct trace of Frobenius. And moreover, we have to prove they actually exist, or don't exist as the case may be. So yeah, so choose correct blow-ups. So first case is the case A equals 7. So such surfaces, as already mentioned, are exactly those which are blow-ups of P2 and 6 rational points in general position. So exactly blow-ups of P2 in 6 rational points in general position. Yeah, so I'd say, sorry, I mean, in this case, A equals 7, Swinnerton-Dyer already solved. But we wanted to give our own proof because we didn't quite follow his proof. So we give our own proof, and I can explain. This proof will also be a warm-up for the other cases as well. So yeah, so then the claim is this exists if and only if Q is not equal to 2, 3, and 5. So what we're going to do is we're going to choose 5 points in general position and then try and find a sixth one, which is in general position for those 5. Anyway. Okay, and if you have any 5 points in P2, they lie in a conic, and since they're in general position, they all lie on a smooth conic. C, but yeah, so over a finite field, any smooth conic, well, any conic even, always has a rational point. There's lots of ways to prove this. You can prove it using Chevalier warning. So they always have a rational point, and as soon as you've got a conic with a point, you know it's isomorphic to P1. And so the number of points on the conic is 1 plus Q. And now you want there to be 5 points in general position. So this needs to have at least 5 points, and this happens if and only if Q is greater than or equal to 4. Yes, so immediately you rule out the cases 2 and 3 quite easily just by looking at 5 points in general position. Okay, now I'm going to consider the union of my conic C with the collection of 10 lines, so where these Li are the other lines through pairs of 2 points. And we want a 6th point, which is in general position to the starting 5, which means exactly we want a point which does not lie in this configuration of the conic in these 10 lines. And you can calculate, it's not difficult, it's just a simple combinatorial exercise, the number of points in this configuration. Well, it's at most 11, you get something like 11q here, because this corresponds to 11 rational curves you've got. But then there's going to be some common intersections which you need to take into account. Anyway, when you do the combinatorics, you find it's 11q minus 24. So the number of points which are not in this configuration, so it's points on P2 minus the points on the configuration. Squared, which you can see nicely factorizes as q minus 5 squared. So I want this quantity to be bigger than 0, and this is 0 if and only if, obviously, q is not equal to 5. So this combinatorial argument explains why 5 is not allowed, but 4 is allowed. Great, so providing q is not 2, 3, or 5, we've got our 6 points in general position. And most of the other cases are similar, there's just different combinatorics involved in each case. So suppose we want to hit trace 5, what do? So we need to blow up some configuration. So to hit trace 5, you need to blow up 4 rational points and 1 close point of degree 2. You can see quite simply this gives a trace 5, and what we show is that this configuration exists over any finite field by just explicitly counting and constructing them. And lots of the other large traces, this works. Here you have 3 rational points, 2 rational points, 0 rational points, and you need to blow up close points to degree 4, 3, 4, 5, and 6. So here we show these all exist overall.
But for instance, when you want close point of degree 6, how do you control that general position?
Good question. So what we do is, so these ones are all constructed by kind of counting, but this one's just an explicit construction. So if you want a close point of degree 6, we take 1 alpha cubed, I think it is, where where fq to the power of 6 is fq adjoin alpha. So we choose an element. Possibly we need more than that, I think. Basically, we need to make sure alpha is a normal basis. Anyway, it needs to be a normal basis. So you take an explicit good generator, which you know, you write down this point, and then you take all the conjugates of it. This gives you a close point of degree 6. And now you ask, how do you know this lies in general position? So there's explicit linear algebra criterion. So you know, if you want no 3 points to lie on a line, this is like some determinant needs to be non-zero. And everything's very explicit here. So you write down this determinant, show it's non-zero. If you want no 6 points to lie on a conic, this is again some linear algebra condition. If you look at the look at the linear system conics which contain these 6 points, imposes some linear condition on the coefficients, which we show isn't satisfied in this explicit case.
I read them examples that realize A equal 5, A equal 4, A equal 3, or it's some if and don't leave statement.
Sorry, can you?
Then that if A equal 1, then the example is given by blow up of like 6.
Oh, I see. Yeah. So I'm saying is, so it suffices to construct to show these collections of points exist in P2. I'm not claiming that every given a trace equal to 1, not every such surface arises that way. Was that your question?
Yeah.
Yeah. No. The thing is, we somehow get lucky. We find some simple examples of surfaces with these traces which exist.
But up to now you managed with non-minimal.
Exactly, yes, yeah. There will be some minimal surfaces with such a trace, but we don't know, well. I'll talk a little bit more about this later. At least for this specific problem, we managed to get away with just showing existence of non-minimal ones, which is nice because it makes life easier for us. Okay, so trace 0, now if you think you can't get it to work by blowing up because you can't get from P2 to trace 0 by blow-ups, but you can usually to blow up and then blow down. So we blow up a closed point of degree 2 and a closed point of degree 5. So this corresponds to so I've got 2 quadratic points which are swapped by action in the Galois, and then I've got 5 points which are moved around in a pentagon. So these are 7 points in general position over, they correspond, 7 points in general position. So this is closed point of degree 2, closed point of degree 5. So then a blow up, I'll call S tilde. So this is not a cubic surface, it's a Del-Petzer surface of degree 2. And the trace of Frobenius here is equal to 1. But now you notice this Del-Petzer surface of degree 2 contains a line, well, at least one line, namely, if you look at the line passing through these 2 points, it's invariant into the action of the Galois group, so it's actually defined over the ground field. But if you look at the strict transform of this line in this surface, it's defined over the ground field. And now let S be the blow down. Of L. So a blowing up and then a blow down, and then this allows me to, just applying this lemma I had earlier backwards, means I can hit the trace of Frobenius 0 I wanted.
You could also blow down the conic.
Yeah. So in fact, these are isomorphic surface because you have this Geyser involution which swaps this line in the conic. Anyway, they give the same surface.
And you can also realize this and blow up of quadratic.
Realize what, sorry?
Blow up of quadratic.
Realize what? S tilde or S?
I mean, if you start with a quadratic, then you have.
So you mean you first blow out the 2 points and blow up the line? It's going to be a quadratic. So it's the same construction, so take a quadratic. The current one, the current one.
Yeah, you take quadratic, pick out 1, and you blow up, what do you need? 4 points, a close point of degree 4. Well, if you want to get S, and if you want to construct the cubic surface S, well, okay, anyway. Yeah, problems with the constructions. The problem with starting off with the quadratic and doing it now is how do you, if you get a collection of points in a quadratic, how do you show the line general position? I mean, this is difficulty. I mean, I don't know what this means explicitly, other than the blob is a Del-Petzer surface. The nice thing about being in P2, you have a very explicit linear algebra condition for being in general position, which you can then verify explicitly. Great. So that's trace 0. Trace -1. This is somehow the first difficult case in that it turns out all such surfaces are minimal. Like, you can't do anything with blow-ups. I mean, they're all non-rational. There's no tricks with blow-ups. So, in this case, you have to use conic bundles. Oops. And maybe I won't talk explicitly about this case because we derived it from a method and known results of Rubikov, who's here. from 2005, and he basically managed to construct some quartic dot Petzer surfaces using conic bundles, and then we just get his quartic dot Petzer surfaces and blow them up, basically. Yeah. And then the last case of trace -2, so this was already handled by Swinnerton-Dyer. So that's a proof. Great.
That's right, so that just guessed the equation, right?
He didn't have an explicit equation. Yeah, I don't know explicit equations for these things. His argument is quite convoluted. He takes some configuration of certain configurations of planes in P3, and then looks at a linear system and then he takes some singular cubic surfaces in P3 given by finite collections of planes. Looks at a linear system, gets a linear system of cubic surfaces, and then he proved just by counting, saying he counts the number of points and the total space, and then says, in order for this to happen, there needs to be at least one cubic surface in this family with this given number of points. So it's completely non-constructive. I mean,
Because the union of three planes contains already too many planes.
something like that. I can't remember his exact argument, but it's definitely non-constructive. Yeah, what Swinnerton-Dyer does. I mean, Great. So now in the last, I think we've got about 10 minutes, which is good. I'll talk about more finer stuff. Okay. So first is generalizations. So great, we did cubic surfaces where you can ask about other Del-Petzer surfaces. We did those as well. So solved analogous problem for all Del-Petzer surfaces. So basically, if you're given a Del-Petzer surface of degree 1 or degree 2, we can tell you exactly what are the possibilities for the number of rational points of any given finite field. There's a list. I won't write it down. It's slightly more complicated, as you would expect, but we've got a complete classification. And the proof is similar. We just hope we can blow up the right number of points and get lucky. And there's a nice trick you can do. Oops.
But I mean, is it at least true that the small p except of 1 is realized?
Well, the problem is it's all about the small finite fields. I mean, this is what the difficulties are. You really want complete classification. So yes, over a sufficiently large finite field. I mean, over a sufficiently finite field, yes, there's going to be 7 points in general position in P2, no problem. But then it's all about really analyzing very carefully these small finite fields and finding exactly where the correct cutoff is. That's what makes these arguments delicate. I mean, okay, so that's one generalization. But you could even ask, great, you solved for trace of Frobenius. So what about more generally asking about all possible Galois actions? So this is, if you like, it's kind of like inverse Galois problem. Okay, so what do I mean here? So I've got S over FQ is a smooth cubic surface. And I'll recall from the beginning of the talk, you've got a conjugacy class associated to this coming from the Galois action of the Frobenius element on the lines, acting on the vowel group of E6 root system. And just so I don't have to keep on writing this, I'll call this group W. Okay, then an obvious generalization of the problems we've already studied is, so I'm going to let C be a conjugacy class. And then the question is, does there exist some S over this finite field with whose Galois action is equal to the given conjugacy class you fixed already? So this is a more finer problem. And we managed to solve this, at least for sufficiently large primes. And moreover, we can even tell you how often these conjugacy classes occur. So it says let C and W be a conjugacy class. And I'm going to let script S FQ be, so taking a very naive viewpoint, it's just a set of isomorphism classes of smooth cubic surfaces So at the moment, we're not doing anything fancy with moduli spaces. I'm just looking at just a set of isomorphism classes. There's only finite many of them. It's a finite set. And then what we show is if you take the limit as q goes to infinity. So I'm just counting those cubic surfaces whose conjugacy class is equal to your given conjugacy class. And then I divide through by the total number of smooth cubic surfaces over this field. Then we show this limit exists, and it's just the size of the conjugacy class divided by the size of the group. So this formula, if you've ever seen the Chebotav density theorem, it's an analog of the Chebotav density theorem, but for counting cubic surfaces. So Chebotav density theorem is about algebraic number fields. And a completely related problem, but anyway, turns out you get the same answer. It's just just the density of your conjugacy class in the group W. So in particular, this shows the inverse Galois problem. It's solvable, providing that your prime power is sufficiently large. Obviously, it's not going to be soluble for very small prime powers, as we've already seen. There's no split cubic surface over F2. But as long as you take a sufficiently large prime power, this means this quantity is going to eventually be positive. And yeah, I'll tell you about the proof, because it's quite a nice proof. This is proof of them too. So we're counting. So in analytic number theory, I start counting, you just sum up your elements weighted by 1. So this is the cardinality on the numerator we're interested in. Okay, so then I'll sum over all cubic surfaces over the finite field. And I'll just weight it instead by the indicator function for the conjugacy class we're interested in. So yeah, it's the indicator function from the vowel group to 0, 1, just telling you whether or not your conjugacy class. Well, I guess maybe I'm abusing notation a little bit here. I mean, when I'm writing C of F's, I guess I mean choose any element in there and then apply it to this function. And it doesn't matter because this function is a class function. It's invariant to the conjugacy. So it's just simply rewriting it. But now, great thing, by character orthogonality, you know explicitly how you can rewrite this indicator function for the conjugacy class. So it's just this ratio which appears in the theorem, and then you sum over irreducible characters of the vowel group. You take the conjugate evaluated at the conjugacy class we're looking at. You take that character and evaluate it at the conjugacy class of S. So this is just a formula for the indicator function of a conjugacy class group, finite group. Yes, yeah. So I'm looking at complex characters. I mean, even though my surface is over finite field of positive characteristic, that doesn't matter. I'm just looking at complex, characters. Okay, great. Now we change the order summation. And we pull out the factor we care about. Okay, so I've changed order summation. So that's summing of irreducible characters chi. So this is just some constant, which we don't care too much about. But I'm summing over the cubic surfaces. And chi of S. Great. And now how it normally goes in these kind of things is the trivial character contributes to the main term. So the contribution of the trivial character gives. So the trivial character just sends everything to 1. So you just get this and then the number of cubic surfaces over finite field, which is great. That's the main term we were expecting. But for non-trivial characters, what's going on? This character, it's just giving you, for each conjugacy class, it's giving you a complex number. And, it could be changing sign. So as I'm summing over these things, I'm expecting cancellation to occur. I've got these complex numbers, just adding them up, some are randomly moving around, expecting cancellation to occur. So here we show that the contribution in this case is negligible, namely it's big O of q to the 3 plus a half. So I should say the number of points. Yeah, what's the total number of all cubic surfaces over a finite field? So how do you calculate this? Well, you need to now start introducing a moduli space for such cubic surfaces. And the moduli space of cubic surfaces is 4-dimensional, just because if you're blowing up points in P2, you're blowing up 6 points, 4 points, you can always choose to just be 0, 0, 1, 0, 1, 0, etc. So 4 points are fixed, and then you've got 2 points in P2, so it gives you four dimensions. And now the number of points on a geometrically reducible variety of dimension n grows like q to the n as q goes to infinity. This is Langbae estimates. So this grows like q to the power 4, which is smaller than the upper bound for the cancellation here. And how do we show this? So thanks most of the work we need is already done by Deline. So we show cancellation curves here using Deline's work on the Loughran conjectures. So I guess this is 1980. So we need to use Deline's proof of the Deline's results on the Loughran conjectures here. And to do this, you interpret this as a sum on rational points on variety, namely a sum over the rational points on the moduli space of cubic surfaces. And once you've interpreted it as a sum of rational points on moduli space of a cubic surface, you have this character. You can input, this gives you some étale sheaf. Anyway, you input it into Deline's machinery, and it gives you this upper bound, which is sufficient for the theorem. Hope it made sense. So maybe I've got like 0 minutes or something left. So I'll just finish by saying, so we solved the inverse Galois problem now for all sufficiently large prime powers, and of course you're like, well, can you completely classify it? So I'll say many special cases of small q, well, special cases of conjugacy classes C constructed explicitly by, so there's quite a few papers, I'm not sure the exact chronology, but anyway, some by Tripalin, who's based here, and also in collaboration with Rybakov. So they've got quite a few papers on this topic, constructing lots of these, and it's almost done. There's basically one conjugacy class. This is just for cubic surfaces. There's one conjugacy class which they can show it exists over half of all prime powers, namely those which are congruent to 1 modulo 3. And for prime powers which are 2 modulo 3, it's not clear yet, but I was speaking with Andre this weekend, and we've got some ideas. So anyway, it looks hopeful that maybe we could completely classify it, but we haven't written it up yet. We've got some ideas. Anyway, so it's very useful coming here because I've managed to actually get some work done. It's quite nice. Okay, thank you.
Do you have similar asymptotic results for del Pezzo?
Yeah. The exact method works for all del Pezzo surfaces. Yeah. So in particular, the statement of theorem is exactly the same. So for del Pezzo is degree 1 and degree 2, we solve inverse Galois problem again for sufficiently large prime powers.
And how explicit is the scope of...
Yeah. Yeah, so I tried to make this explicit. It's quite difficult. I mean, there's lots that goes into this. The thing is, Deline's estimates are explicit. You just have to calculate these cohomology groups and the dimensions of them and things, all these sums. So yeah, I think it could be made explicit, this big O. Like the Hasse estimates are completely explicit. Why can't I make this explicit? So I think it could be made explicit, but the bound you get here would be really large. And I don't think it'd be realistic, say, for a computer to try and fill in the small prime powers, which I was thinking, but I don't think that's realistic. I don't know. Maybe you get something, you could get something the size like 1,000 here. That's not realistic, but still, the computer wouldn't be able to handle, wouldn't help with that.
If not, let's thank the speaker. We have tea break for 20 minutes.
On the ground floor over there.
Okay.